So in this class, we will be discussing about the compensation techniques. So first, we will consider the circuit stability. So if you consider a normal feedback circuit with op-amp, the negative feedback. That Now, if you consider this kind of a network, this network consists of both forward block as well as feedback block. So it has forward block, which means that without that feedback connection, if you consider it is just a forward connection. So that connection is called as forward flat, and it also has one feedback block. Feedback block. This can be more easily understood by plotting this in an equivalent circuit. So we will be having one feedback network as well as one forward. And as the feedback block uses only that resistive elements in this particular circuit, so its transfer function is independent of frequency because you do not have any capacitor in this circuit. So the transfer function will not depend on the frequency. So only that because we have only that resistor components in the circuit. Okay. So as the feedback block, as the feedback block uses only resistors as a resistive elements. So the transfer function transfer function does not depend on frequency. Now, as you know, open loop gain will be given by open loop gain equal to will be given by A0 L equal to the output by V difference. When you do not have that closed or feedback circuit, your circuit will become open loop circuit. So that gain will be given by A0 L, sorry, AOL, which is equal to VO by VD. VO is the output voltage and VD is the differential voltage between both terminals. This thing we already covered in the previous classes, so we will not go to the details of these equations and these terminologies AOL. Then we have that feedback gain that is given by this closed loop gain, closed loop gain given by AF, or you can take it as SEL. Both are same. So that will be equal to V0 by V in AOL divided by, that is open loop gain divided by 1 plus AOL. Okay. Now, by using this equation, the stability of the op-amp configuration that we have here, or the circuit, the stability of this circuit is depending on this root of this particular term, which is in the bracket. Suppose that A0 L beta, if it is going to become -1, for example, then the denominator will become 0 and the total term will become infinity. That is 0 by will become infinity. So the root of this particular equation, 1 plus A0 L beta, depends on the circuit stability. So we can from here the stability of circuit, stability of the circuit uh, depends on the behavior of roots of 1 plus A0 L beta by root of equation plus A0 L beta. I make say to say 0 and this is A O L properly. So this 1 plus A O L beta, which is equal to 0. So the characteristic equation is this 1 plus A0 L beta equal to 0, and find out what is the roots, what are the roots of that equation. That will determine your stability of your system. In other words, stability of the circuit means that dividing, or we can say stability of the circuit can be also, we can define it in terms of how close this circuit is to the condition of sustained oscillation. So we already discussed that we are talking, or we need the amplification in the circuit. But if your amplifier is having some particular condition, which is the oscillator condition, okay? So in that case, we cannot get a constant output at the output end, or constant voltage at the output end. Instead of that, we will be having some oscillation. Okay? So if your gain values are having some particular condition, which is called as the bar cosine condition for oscillators, as we have studied. So that condition is nothing but if you are having that A into beta, which is going to become 1, this is going to become 1. Then this magnitude, and along with this, if you are having that phase shift of 180 degree, then the amplifier will become an oscillator. Instead of an amplifier, it will become an oscillator. So we have to do some compensation technique or compensation to avoid this condition. For example, if it is having some 180 degree of phase shift, or something which is close to that range, which means that if it is having larger phase shift, then we should not have this condition at that particular frequency. So if at a particular frequency f, if it is having close to 180 phase difference, then this A beta value should be less than 1. Okay. So in order to do that, we have to reduce the value of gain, open loop gain. You have to reduce. Then we have to we need some other kind of arrangement in that circuit in order to reduce the gain, so that the value of A beta will be less than 1. So if it is less than 1, it will not become an oscillator, because the first Bark-Rosen criteria will not be valid in that case. So we have to use some other circuit to reduce that gain. Otherwise, you can use some compensation technique and reduce change the phase of this. So normally we will reduce this gain in such kind of situation in that particular frequency where you have phase differences which is very large and close to that 180. So for otherwise it will become the amplifier will be having some oscillating effect or oscillation in the output. So the amplifier will become an oscillator and the stability is compromised, or we can say the stability will be very less of that circuit. So in order to have a stable output, we have to do this compensation. Okay, so we'll continue here. Okay, so stability of circuit, we can also say that how close the circuit is to the condition of sustained oscillation. How close the circuit, I would write CKT instead of circuit. So how close the circuit is to the condition of sustained oscillation. So by means of that also we can define the stability. So the system is said to be stable if the output reaches a fixed value within finite time. Within a finite time, if the output is reaching a fixed value, then we can say the system is stable or the circuit is stable. System or the circuit is said to be stable if the output reaches fixed value, fixed value, fixed value within finite. We can also define this, for example, the critical values of gain and phase are 0 dB and minus 180. So these are the critical values, which means 0 dB means that the gain gain will become 1 unit. Okay. So the gain will become 0 dB means the gain will become 1 in normal units. This is in dB. In dB is 0 dB. So under this condition, 0 dB and minus 180 degree, these are the critical values of gain and phase for this stability. So this This can be expressed in terms of gain margin and phase margin. So gain margin, we already discussed in one class about the gain margin and phase margin. So the gain margin GM is given by minus 20 log AOL into beta, this much of dB. Okay. So this much of dB. And also phase margin be given by phase margin equal to 180 degree plus angle of AOL into beta. So if your phase margin, if your phase margin under this condition, these two are the condition. If EM, you can write that in terms of phase margin also. So if GM and PM are negative, then the circuit is unstable. This is the stability condition. These are the stability conditions. So if you calculate this gain margin, similarly the phase margin, this is nothing but you have to take the product of this AOL in beta of your circuit and find out what is the log of that term and into 20. So what is that value? So if this value is coming something which is point and log of that value is coming to be negative, in such cases this GM will become positive, so that the circuit will become stable. But in some other cases, if you take this log of A only in beta, okay, then that will become positive term, so that the total gain margin will become negative. If the gain margin is negative, that means the circuit is unstable. Otherwise, if you consider here the phase margin, and the phase margin, if this phase margin is going to become negative, for example, then in that case also the circuit will become unstable. When this will become negative, this term angle of or phase angle of this AOL beta, that should be in this case it should be less than, no, it should be greater than minus 180, right? It should be greater than minus 180. So under that condition, this phase margin will become negative. If it is, for example, minus 200, this value is going to be minus 200 or something, then this total value will become negative, phase margin will become negative, and your circuit will be unstable. So these are the two conditions when you will get when your circuit will become unstable. And this, by using these two equations, we can say that whether the circuit is stable or not. Stable means the circuit will be having the same output as we designed for the amplifier. But when it is unstable, then it will become there is some oscillation effect at the output. So the output will not be constant value for given condition at the. So that will become an oscillator. So the circuit stability is defined by these two conditions. You can also look this by considering that Barkhostein criteria, that is A beta, modulus of A beta should be equal to 1, and the phase difference should be 180 degrees or plus. In that condition, the amplifier will become an oscillator. Okay. Now we will discuss how we can remove this kind of circuit instability that we have to study. Then we have to focus on that. So for that we have to use frequency compensation. Then we have to use frequency compensation. So in frequency compensation, if you consider this, so this is used, as I already told, this is used uh, to reduce that kind of problems or that kind of instability in the circuit. Okay, so this is to stabilize. You can say this is to stabilize stabilize the circuit. I'm writing it very shortly. You can elaborate that if any such problems, such kind of instability present in the system, in the circuit, then we have to compensate those problem at that particular frequency, and then we have to use frequency compensation technique. Like that, uh, you can make it a sentence. I'm just writing very short. So this is to stabilize circuit, which means that we have, if any such kind of problem, any such kind of instability present in the system, in the circuit, then you have to stabilize that those problems in the circuit, and since techniques are there, so we have to use any of that to compensate the problems which is in the in your system of the circuit. So for that we have to use frequency compensation techniques. Okay. Now in this technique, okay, the op-amp circuit with single break frequency, the op-amp circuit with the single break frequency, single break frequency, or we can also say that the corner frequency or corner frequency. This is the frequency at minus 3 dB less than that of maximum gain. We already discussed. So this is the when the op-amp circuit with if you are considering op-amp circuit as a single break frequency, in that case the circuit will be inherently stable. Okay? So the op-amp circuit with single frequency or common frequency will be inherently stable. So if your op-amp is having only a single break frequency or corner frequency, which means that if you take that frequency response curve with gain versus frequency, and if your op-amp is having something like this, and you have only one break frequency at this point, where you have that a minus 3 dB, 3 dB gain. Okay, so in that you have that break frequency or the corner frequency. So that is if only one corner frequency present in the system in a circuit, then that circuit will be stable. Okay, this is inherently stable. We do not have to consider these kind of frequency compensation. But there are some cases we will be having different number of corner frequencies, and the circuit will become unstable in some cases. Okay. So the frequency compensation technique normally we use this you can say frequency compensation. So this frequency compensation we broadly classify into many groups. We have to get stability, which means that we have to get larger bandwidth, you get larger bandwidth, larger bandwidth, bandwidth with, this is a single word, okay. Bandwidth with lower closed loop gain. Closed loop. And secondly, second one is uh, to alter the response, to alter the response as per the requirement. You'll understand what are these things very soon. There are two important things we have to get after this frequency compensation. One is to get the larger bandwidth within a very close, very low closed loop gain, and to alter the response. If you want to change the response of this particular op-amp circuit, frequency response of this particular op-amp circuit, then we have to use this compensation technique. Then we can arrange this gain and frequency or gain of the system with different frequencies. These two are the important functions that we expect from the compensation. Okay, so there are mainly two different kind of compensations. One is called as internal compensation. So this we already discussed. Internal compensation, and then we have external compensation. Then okay. I hope you can hear. So we have two different kinds of compensation. So we have two different compensation techniques here. Let's see. And one is internal compensation, another one is external compensation. We already discussed about this compensation. We had studied the different op-amps in initial classes. So internal compensation is that the compensation will be done inside the op-amp itself, and the external compensation will be we have to use some external circuit in order to compensate. Yeah. So that are that's the difference basically different. And we will be more focusing on this external compensation. In that we have two different techniques. One is the dominant pole compensation. Dominant pole compensation. So first we will discuss with the dominant pole compensation. So in this external compensation, we have two different compensations. And in this dominant pole compensation, we have to consider an amplifier, for example, consider three three break frequencies. വോയിസ് വരുന്നതല്ല. ചിലപ്പോ റേഞ്ചിന്റെ പ്രശ്നം. ബ്രേക്ക് ആവുകയാണെങ്കിൽ റേഞ്ചിന്റെ പ്രശ്നം. എല്ലാവർക്കും ഉണ്ടോ പ്രശ്നം? ഇപ്പൊ ഉണ്ടോ? കേൾക്കുന്നുണ്ടോ? ഹലോ,
ഇപ്പൊ കേൾക്കുന്നുണ്ട്, പക്ഷെ സ്ക്രീൻ കാണുന്നില്ല.
So let's consider for this dominant pole, let's consider a three break frequency system. An amplifier with a three break frequencies. Frequencies. So and loop gain is A. Let's say loop gain is A. So this loop gain will be given by open loop gain divided by 1 plus J into F by F1. The F1 is the first break frequency. Then 1 plus J into system, this circuit which is having gain, and this circuit is having three different break frequencies: F1, F2, F3. These are the break frequencies. That you can get from here. This F1, F2, F3 will be providing the poles of the system, and that's why they are the break frequencies, or we can say corner frequencies. Now, if you consider such kind of system, and if you want to apply dominant pole compensation in that system, then instead of your normal op-amp circuit, you will be having circuit like this. So this is your normal op-amp. So we have a V input here. So we have V input, and this is your V0 dash. That is the output that you will get after this op-amp, and you have gain which is equal to A, loop gain of A. So I'm not drawing those feedback and all those things. This is just representing that this is your amplifier, so that you have a loop gain of A. So this is with the loop gain. So without loop, that feedback we have open loop gain. With that we have loop. So this is a closed network, closed circuit, closed circuit with feedback. So with that we have a gain of A. So if you provide input V in with within to into this op amp gain A, then we have output V0 dash. Okay? And this V0 dash we will be given to another network which contains a resistor as well as a capacitor like this, and we will take the final output after this components. This is your final output. So this is the dominant pole compensation. So in order to have this dominant pole compensation, we need to add a capacitor resistor components, capacitor and a resistor into system or into the circuit. And this particular network is called as compensation network. Compensation. So this is for dominant pole compensation. So for dominant pole compensation, dominant pole compensation is introduced by adding a compensating network of resistor capacitor. So we have to add this particular network to your op-amp configuration. Then your circuit will be compensated under domain pole compensation. Okay. So what is the meaning of this dominant pole compensation? Dominant pole compensation means that the pole with the magnitude much smaller than the existing pole has to be added into the system. Okay? So that is the dominant pole. We already discussed about this dominant pole concept when in the last class. So dominant pole is nothing but a pole which is having frequency which is much less than the existing break frequency. Okay? So dominant pole means dominant pole means the pole with magnitude magnitude much smaller than the existing poles. So if there are many poles which is already there in your system, in your circuit, which means that it will contribute to many like frequencies. And then if you want to add a dominant pole, that its magnitude, which means that its frequency has to be much less than that of the, or it should be less than that of the existing pole. Okay? That is the dominant pole, and dominant pole is we can define that as which means that the pole with the magnitude much smaller than the existing pole. That we have to add by using this compensation, this dominant pole compensation. Okay. Yeah. So if you consider the break frequency of this uh, compensating network, if you want to calculate what is the break frequency of this compensating network, that means this RNC network. Okay. Uh, so this has to be smallest compared to the existing break frequency, right? So if you calculate that, so the break frequency. So what we have done, we added an additional network to the op-amp circuit here, and that particular network is called as compensation network. Once you add this compensation network, then which means that your circuit is compensated with dominant pole compensation. And dominant pole means that the pole with magnitude much smaller than the existing poles, which means that if you are having this circuit, then that should give you a break frequency which is smaller than all the break frequency already there in your system. So if you want to calculate what is the break frequency of this particular network, that compensation network, so the break frequency of compensation compensation and this particular frequency has to be smaller than all other break frequencies. That will be given by, let's say this is let's take this A1 is AX R minus X. This is the gain uh, we have to calculate at this voltage. Okay. And if you further consider this, actually that will come as you want to, that will be something we have some input here and we have output here. So if you take the ratio V out by V in, then V out will be this much. We have to consider potential. So that will be given by this resistance R. So in that case, if you consider the reactance of the capacitor as minus Jx, then this will be given by, for example, if you want to calculate the out equal to minus Jxc by R minus Jxc with that potential divider method, and this will multiply with the whatever input is coming to that branch. Okay? And if you take this V in to this side, this V out by V in, that is Xc R minus what we have. So that is the gain of that compensation network. And this can be again written as minus J Xc is 2 pi Fc. Then have here also R minus A by pi C. can be again reduced as minus j by 2 pi. Or I can simply you can write. So this can be written as 1 by r by will be equal to r divided by minus j by 2 pi f plus 1. So this is the expression for a1, and also if you take 1 by right, but 1 by j by minus j is equal to j, or minus 1 by j. So this implies a1 equal to 1 by, so this minus j can take to the operator. So that will become 1 by, also that's so this will become 1 by 1 plus j 2 pi times r f c j into 2 pi times rf c, because when that this term also getting right. So this is a total of that gain after reducing uh, simple form. So this is the gain produced by the compensation network. So I hope you know this, how this is coming. Uh, you can take this into denominator, take this and this one will be cancelled, and that will become 1 minus that will be plus 1, and then you will be having, here we have r by minus by m. So that's how term is done. And you are having this as your compensation network gain. Further, if you reduce this as consider, or suppose AD equal to D equal to 1 by pi RC. Let's consider, sorry, not AD. So this is FT. So let's consider T equal to 1 by 2 pi R. Then your A1 will become 1 divided by 1 plus J will be there. Okay. Then 2 pi RC will become 1 by FT, because FT is 1 by 2 pi RC. So this will become F divided by. So this is the gain of your compensation work with FT equal to 1 by 2 pi RC. Okay. Hence, we can say the compensated 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 transfer function right? A dash, let's say this A dash will be equal to A times A1. Okay. So I'm talking about this transfer function. So that will be given by A dash is equal to AOL divided by So you have this expression. Why this is multiplied with this A1? Because we are having that circuit which is connected seriously to your network. So we have to multiply those two to get the total. So now we have A already. We have A without compensation. We already defined what is A without compensation. Let's consider. Yeah, here. So you have this uh, A with without so this is the transfer function without that compensation. Okay, so this is in here we are just considering your op-amp circuit with the three peak frequency, which is not compensated. So this is the transfer function for the uncompensated circuit. This is an uncompensated circuit. Okay, so that compensated because we didn't apply any compensation to that system. After that only we are applying this technique for compensation. So this is the transfer function. This is the transfer function of uncompensated circuit. Transfer function of uncompensated circuit. So after compensation, how this transfer function is going to change, that we are going to do. So we have to consider the total transfer function as A dash, which is equal to A into A1. So this is nothing but AOL into. Then we have 1 plus J into F by F. This is coming from this equation because A1 equal 1 by 1 plus J by F. Then we have all other terms J into F by F1 and 1 plus J into F by F2 and 1 plus J into F by. And this Ft, value of Ft has to be less than all other break frequencies, F1, F2 and F3. And we have to choose the RC values in such a way that the Ft value is much smaller than the other form of frequencies. Okay. So here value of R and C are chosen in such a way that Ft is smaller than all other frequencies. Okay. So R and C we have to choose in such a way that Ft is because Ft is 1 by 2 pi RC. We already have that expression here. So we have to choose R and C value in such a way that it is giving a value of Ft which is smaller than all other break frequencies. That is the condition for this dominant pole compensation. So, so what is the result of this particular compensation technique? So that we will discuss with the speaker, but it is not having that clarity. Anyway, I will explain this. So this represents ACL. ACL, this axis represents ACL. ACL means closed loop gain, or you can write it as AF. Or you can put it as ACL in the closed loop. So closed loop gain is ACL, and that is equal to that is given in this y-axis this is something 80, 60, 40, 20, and this is in dB. Axis here you have 0 dB. Here you have in this axis you have frequency f, x-axis. So this is your first cut of frequency f1, f2. We are just any change in our gain. We already told in the last class how this can be converted into dB and all those. So in the first line we get 20 log of a0 or a0l of in case in AOL that we will be getting. So this will become a constant value, and minus we'll get all other terms, and in the all other terms we'll be having different. So this minus terms in this case we will be having three minus terms x, y, z corresponding to this break frequencies f1, f2, and f3. Okay. So this we already discussed this in the last class how we can convert that uh, equation into dB, how we can see that of our gain. So in first case we have 20 log a, L is a constant, open loop gain is a constant, and we will get the constant value that is this line 20 log a, L or a0 we can consider. So this is the constant part, and once you have this first big frequency has reached, because of this have a rate of minus 20 dB per decade. This is minus 20 dB per decade, right? So that will start decreasing like this up to f2, and f2 also produce a minus 20 dB per decade decrease in gain. So total will be minus 40 dB per degree per decade when it reaches at f2. So from f2 to f3 it is having this minus 40 dB per decade. So then from f3 we can have 60 dB minus 60 dB per decade is of gain. Okay, so that is what you can observe here, and this one is uncompensated, uncompensated. Right. So this is uncompensated, corresponding to the uncompensated frequency response of the uncompensated circuit. This one, this black what you have, and this one is the compensated. So right here, compensated. So this is for compensated case, compensated circuit frequency response. So what happened here? So we have in the first case we have a bandwidth up to this point, where you have that a break frequency which is around this point, okay? Because you have to consider the minus 3 dB of the maximum value. So if you consider this as your 3 dB, this would as your 3 dB. So let's consider this width as your 3 dB here. Okay. So if this is 3 dB, this much of value, which means that from the maximum value of gain ACL, which is reduced to reduced by 3 dB. So it is reduced by 3 dB in this. Okay. So from that maximum value, it is going to reduce by 3 dB here, and what that 3 dB gain, which means that ACL minus 3 dB value, then here you will get the corner frequency. So if you take the frequency corresponding to that value, where your maximum frequency is reduced, sorry, maximum gain is reduced by minus 3 dB. That is your corner frequency. So your first corner frequency will be at this one. Okay. Correspondingly, so this is the corner frequency when you are having when your circuit is not compensated or uncompensated. Okay. And up to that we will be having the bandwidth. So initially we have bandwidth from this 0 to this much of frequency. We have bandwidth there we bandwidth 1. So the bandwidth will be larger in that case. And if you consider the compensated network, what will happen? You will be having an additional pole in your system. And when you are having that additional pole in your system, that is FD. Okay, so then your equation will be having some one more uh, pole in your system. Then that FD is the additional pole, and that will make an additional break frequency. So this is your FD. So this is your FD here. This point. So this is over here. FD value is represented as in frequency axis. So this one is your FD. So if that is the FD value, and if you take the 3 dB, then your break frequency will be at this position. Okay. Then you'll be having a break frequency at this position, which means that from here itself it is going to start decreasing by a rate of minus 20 dB per decade, as you can see from here. And once it reaches at this F1 position, that is the second break frequency now. Okay. And then you will be having you'll be having another decreasing of minus 20 because of that F1. So here we will be having minus 40 after that F1. So from the break frequency, so here we have the break frequency F1, and here we have the corner frequency, which is minus 3 dB from the maximum gain. So the break frequency we have here when with the compensated network, that is first break frequency is attained in this position, or you can say at this position. And we have an additional corner frequency around this point. So we have a corner frequency at this point in that case. So the bandwidth will get reduced here. Bandwidth is CW2. So the bandwidth is reduced in this case, which means that when you have that dominant pole compensation, your bandwidth will get reduced as compared to the uncompensated circuit. But an important thing is that we have to consider here is that our gain will be reducing to zero. Gain will be reducing to zero very smoothly when you are having that compensation. But that is not the case when you do not have that compensation. When you consider the uncompensated network, then we have different kind of decreasing of gain corresponding to those break frequencies. Okay. You can see from this figure, the decreasing of the gain is not linear, or it is not a good response. But when you consider the compensated network, then the decreasing is having some constant rate, or the stop is constant. Okay? So it is having some good response with respect to frequency. That is the first important thing that we have to notice. Also, we can consider the gain and phase as we discussed the Barkhausen criteria A into beta. So this has to be one, magnitude of this has to be one at with the phase shift of 180 degree. Yes, here it is minus 180 degree. So under this condition, that will become an oscillating effect or oscillator. The circuit will act as an oscillator. So this will be at some frequency. This is at some frequency. This condition will be achieved, and the amplifier will become an oscillating or oscillator. And then if we want to change this condition, or if you do not want that this oscillating effect in the circuit, then the what we have to do, we have to reduce this A value. If you reduce this A, then A into beta magnitude of best value, this should be less than 1. So we have to reduce A in such a way that A into beta, this value has to be less than 1. Okay, then that bar cosine criteria will not valid, not become valid, and the circuit will be prognosed. So in order to reduce the gain, we can use this compensation technique, because as you can see from here, we have a large gain in these frequencies also, as you compare to the other cases. So, but when you consider in this range, if you consider, for example, this frequency happen to be in this range of frequencies in between these two, between this FD and F1, then there we do not, for example, if you want to reduce this gain, then we can have a less gain at these points. Okay, less gain values at these points in between FT and F1. But that is not the case when you are having that uncompensated network, because you are having a constant gain in that region. Then you cannot reduce that gain, which means that your A beta will be equal to 1 or more than that. So in that case, we'll be having that oscillating condition. If it is going to be 1, then we'll be getting that. So if you want to reduce that, you have to add one additional network QC system in order to compensate the circuit. Uh, in this case, it is a dominant pole compensation. And because of the dominant pole compensation, your first form of frequency, sorry, first break frequency is going to be shifted towards lower frequency, and the gain will be reduced from there itself. Okay, so that we can also have a reduction in gain, and we can adjust the cosine criteria, and circuit will become complete. So it will be having constant output. It will not. So this is the compensation technique that we use under the dominant pole compensation technique. And then what actually we have done here, I will just show a representation of the same in order to get the picture of the dominant pole compensation. I will just represent the same here. So what we have done, we have a curve without compensation initially. So let's say this is your gain, and this is your frequency F. This is your maximum gain. Just putting it there. And this is the closed loop gain in dB, your frequency. Okay. And let's say this is your 0 dB time. Your 0 dB. From here you have 10 dB, 40 dB, and so on for your gain. So your gain will be constant for some value up to that first break frequency. So once that first break frequency has reached, means that the first break frequency for uncompensated case is F1. That is start decreasing with the rate of minus 20 dB. And when it reaches to the second break frequency, that is F2, it will again start to decrease by minus 20 dB. And together, the first and second minus 20 dB, we have 40 dB per decade. So this is, let's say, this is just at this point. So this is 30. And then it starts decreasing with minus 40 dB per decade, minus 40 dB per decade. And the third frequency, that is F3, 3. Okay. So then after reaching that third break frequency, then you will start again. Right. So here it is minus 20 dB per. here it is minus 40 dB per decade, and here it is minus 60 dB per. Okay, this is the frequency response without compensation. Once you introduce that dominant pole compensation, what will happen? In that case, dominant pole compensation, once you introduce with the proper R and C value, that frequency, that break frequency has to be less than the all other break frequency, which is already in that circuit. So it should be less than F1, F2, F3. So somewhere here, let's say your FT is somewhere here. Okay. So you have FT here. This is your FT. So with the compensation, your first break frequency happens at this point. As you can see. Okay. Now, if you want to, for example, okay, if you want, this is not the exact figure what we have here. Anyway, I will do that in parallel. So somewhere it will make somewhere here. So, no problem. We will take it like this. So if you are having this FT, then it will start decreasing from here with the minus 20 dB. So this I'm not going to write in the exact. Here. This is somewhat different from the previous curve. Anyway, so it will start decreasing with the minus 20. I'm just taking the same slope of this one, so it will not be matching with the previous figure, but I will explain how it is coming. Okay. So it is going like this, and when it reaches at this point, so because of that additional break frequency, the frequency, sorry, the gain will start decreasing from FT itself. Okay, and it will reach at the F1, point F1. At F1 we have the second break frequency. In this case, after compensation, we have second break frequency at F1. So from there, it will start decreasing by minus 40 dB per decade. So it will be having this minus 40 and so on. Then after reaching at this point, it will be having minus 60 and minus 80 also. So what is happening here is that our first break frequency that is reduced. So where it will come the corner frequency, because the corner frequency will come here at as we are taking this point as SEL minus 3 dB. Maximum gain divided by, sorry, maximum gain minus 3 dB. So corresponding to that, what is the frequency? That will be your corner frequency. So at first we have the, sorry, at this point here, and what is that frequency that you have? So this point is the break frequency, that particular, sorry, the corner frequency. So this is the corner frequency where you have a minus 3 dB gain. So this is the corner frequency. So this is the corner frequency, so that you will get a bandwidth of this much in the uncompensated circuit by using that uncompensated circuit. But in the second case, when you are having that compensation, this minus 3 dB, a minus 3 dB will be at this point, and you will be getting a bandwidth up to this point. This is your corner frequency now, and you will be getting bandwidth up to this. So the bandwidth will be getting reduced after dominant pole compensation. That is a disadvantage with the dominant pole compensation. Okay. But if you are considering, for example, that Burke-Hossein criteria, which is happened to be somewhere in this region, between somewhere in this region, then that we can manipulate. Okay, because If you do not have that compensation, then your gain is constant in this region, as you can see. Gain is constant in this region, and your product A beta will be equal to 1 or more than that in that particular case. So we will be having some oscillating effect. If the phase shift is happen to be around that 180 or more than that. Okay. So if it is having a phase shift, for example, 180-degree in this region, and you are having that particular having a phase shift of and also we have a gain which is larger and a beta is equal to 1, somewhat similar to that, then you will be having some oscillatory effect at the output. Your amplifier will become an oscillator. So if you want to reduce that gain in such a way that your A beta is less than, A beta will become less than 1, as I discussed earlier, A beta has to be less than 1 in such a way that your A has to be reduced to avoid that Barkhausen criteria. So in the uncompensated case, we cannot do that because you are already having 180 minus 180 phase shift in this point, and then you are having a beta value which is equal to 1 at this point. So then you introduce one compensation network in your circuit, and that is by dominant pole compensation technique, for example, and that will make one more pole in your system, which means that you are making one more break frequency in your system. That will be less than that of F1, F2, or other higher break frequencies, and your gain will start decreasing from this point. So in this condition, you will be having a beta which is less than 1, even though you will be having minus 180. So by that means we can control or we can make our circuit stable. Okay, so that is what is the function of this compensation network. So if you want to know these advantages of this dominant pole compensation technique, consider the advantages first. So the advantages of dominant pole compensation we already discussed. So first I will just write it shortly. So advantages of dominant pole compensation. I'm talking about these advantages of dominant pole compensation. So in that case, we have very less noise. We can say noise impedance is high. In this case, because our bandwidth is small and normally the noise frequency components will be outside of this particular band. So because of that, noise impedance is high, which means that the noise will be low. I'm just pointing out two important advantages. You can search for further advantages of this dominant polarization. And then adjusting the value of Ft. That will give you adequate phase margin and gain margin, adequate phase margin and gain margin, and the stability of the system assured. So by adjusting that adjusting FT value, this by means of adjusting that R and C values in the compensation network, we can have some adequate or appropriate phase matching and as well as phase margin and gain margin. But then that will result in the stability of the system. So these are the advantages of the dominant pole compensation. Also, there are some other advantages. The external compensation, there are some advantages because of that. So you can list all those things. Okay. Then we have one disadvantage in this case. Disadvantage, which is the bandwidth reduced. Bandwidth reduced drastically. So in this case, we do not have that much of bandwidth. Bandwidth reduced drastically. So as you can see here, bandwidth is this much. Why? But here we have only bandwidth of this one. So if you are introducing a dominant pole, which means that if you are using this dominant pole combination, then you are introducing a dominant pole, which means that you are adding one more frequency before all other frequencies, and the corner frequency will be associated with that one. Then obviously the bandwidth of the op-amp. So that is the disadvantage of this particular. There may be some other disadvantages. Now we will look into another kind of compensation technique. So this is also coming in the external compensation. This is the second technique in the external compensation. This is called as pole zero compensation. Pole zero compensation. So in the case of pole zero compensation, what is happening is that we have to introduce a pole as well as a zero. Okay. So in this case, we are compensating. It's nothing but compensation of compensation of a pole. And so let's again consider op-amp with three break frequencies. Three break frequencies. So A will be equal to AOL divided by 1 plus J in the F1. Then we have 1 plus J in the F by F2. F1 plus. So after this pole zero compensation, also our transfer function will be modified. Okay. And remember that the zero is added. Zero added a high frequency. And this may confuse you, so I will not. Basically, that zero will be added with the frequency which is larger than that of the first pole, which means that whatever the pole that we are introducing. Okay, anyway, the pole zero compensation, in pole zero compensation we have circuit diagram like this. So this is our V in, this is the amplifier with the gain A. Then we have that zero dash, and then this is going through one resistor, another resistor here, then a capacitor. So unlike the previous circuit, we have two resistors here, one resistor before this capacitor, and then we have this output. So this particular compensation, this particular network compensation, this pole zero compensation, and this resistance R1. Let's assume it as C2. because of that branch. So R1, R2, and C2 are the components, and this part of that network is called as the pole zero compensation. Now, if you want to calculate what is the gain because of this network, so the gain will be A1. So this is the gain associated with this network compensation network. So that will be, in this case, that will be equal to V0 by V0 dash, and that will be given by A1 equal to what this will result will be equal to R2 minus JXC divided by, so here is XC, and then we have R1 plus R2 minus JX. So this is the gain that you will get A1 as your A1. This is just that voltage divider rule. You have to take this resistance, total resistance, this branch, R1 here. So this total resistance will be R2 minus JXC2. That is what we have written operator. Then divided by R2 minus, sorry, R1 plus total resistance, R1 plus R2 minus JXC2. Actually, it will come as if you want to. So this will be, here we are calculating what is the potential at this point. That will be equal to V0. Okay. So V0 is this much times V in, or V0 dash. This much times V0. Okay. 0 equal to R2 minus JXC2 divided by R1 plus 2 minus. So this much of term times V0 dash is V0. And we have to take V0 by V0 dash, then these two things will get cancelled. Only this term will be remain as per T. Okay. No problem. So this is the gain associated with this particular compensation network. This we can further reduce. Okay, I will write. Okay, this is equal to A1, which is equal to one thing. Okay, this is R2 minus, you know what is XC2, so that is J divided by XC. X is 1 by 2 pi. That's, so this is J divided by 2 pi F2, and this divided by R1 plus R2 minus J divided by pi. Remember, this C2 is expression and this C2 is value. Now this can be further reduced as R2 divided by, like, minus J by F plus 1 divided by R1 plus R2 J by FC plus 1. This two can be cancelled. Now this will be implies A1 equal to So this minus j can go up, become plus j. This 2 pi fc2 also go up. So it will result in 1 plus 2j pi, or you can write j into 2 pi plus R2 divided by 1 plus R1 plus R2, you can take as common. FC2 times 1. So this is the final expression. That minus j we have to take in numerator, and 2 pi FC2 also we have to take in numerator. And we'll get expression like this. And if you consider uh, the condition that two conditions we have to apply here, because we have two terms. So if 2 pi FC, all right, if f0, let's say f1 equal to, okay, if f1 is equal to 1 plus or 1 by 2 pi f into R2 C2, and f0 equal to 1 by 2 pi f into pi f2 to R1 plus R2. Okay, so these two are the frequencies f1 and f0. If you are considering like that, then your A1 will become, your A1 will be 1 plus j into plus j into, sorry, this f will not be there. F will not be there. So f1 is equal to 1 by 2 pi R2 C2. And here also we have 1 by 2 pi R C. And then we can write 1 plus j times f by f1 here, right, divided by the numerator. In the denominator, we have 1 plus j into f by f. So these are the, this is the gain which is produced by the network, compensation network, with f1 equal to 1 by 2 pi R2 C2 and 1 f0 equal to 1 by 2 pi C2 times R1 plus R. Now, with this compensation, we can write transfer function. So total transfer function, how we can write? So total transfer function become, as we already discussed, it will be, let's say a dash equal to a times a1. This will be equal to, so we have in numerator, we have initially a0l. Yes, have a0l in the numerator, right? So in addition to that, we have one more term in the numerator from this 4-0 compensation, because we have one more numerator term here, a1. So multiplying that, so a0l into this term also will come 1 plus j into f by f1 divided by, then we have 1 plus j into f by f0, that is the first one. Then we have 1 plus f by f1, j by f1. Then 1 plus j into f by f, also 1 plus j into. Now what will happen? Now what will happen to this equation? Because we have same term in numerator as well as denominator, so these two terms will get cancelled, and the resultant a dash from a0 divided 1 plus j into f by f0, 1 plus j into f by f1, sorry, f1 will not be there, f by. Still you are having that three break frequencies, but the break frequency f1 is cancelled. This is what will happen when you import. Because of this numerator value of f1, that is the first break frequency in the uncompensated circuit is cancelled. And in addition to that, we have additional one more break frequency, which is f0. So from figure, we will explain that. So this is the figure that representing the compensated and uncompensated frequency response. So here we can see that this is, for example, this is the maximum value. Should be AOL, right? This is also AOL because we already taken A equal to AOL by that quantity. So represent it as AOL open loop. Okay, take that. Okay, probably that is maximum gain that we. And here we have this AOL particular figure, and this is 80 dB, 60 dB, 40 dB, and 20 dB. 0 dB. Set gain equal to 1 in normal units. When you can convert it into dB, then it will become 0. Okay, so this is the response for response curve, frequency response curve. So from this we can see that initially if the system is uncompensated, if the system or circuit is uncompensated, then we will be having three different frequencies, break frequencies. One here, this is f1, f1, and then we have second break frequency, which is at f2, right? And third one, which is at f. Okay. Then if you consider the case of bandwidth, before that we'll discuss about the compensation. So uncompensated case, we have minus 20 dB per decade, minus 40 dB per decade, minus 60 dB per decade, as we discussed in the dominant pole compensation. Same kind of figure we can get here because there is no change in that case. But in case of a compensated network, we have an additional pole here at this f0. Have additional pole at f0. And remember that there is no variation in your slope once, even if it is reaching at f1. Okay, and it has been increased, that this width has been increased, and once it reaches f2, then only it is going to decrease by minus 40 per, after reaching that value of thing, this has to be little deviated because f2 will be there. Okay, so if I plot it in the previous curve, so this is the new pole that is in your circuit in the uncompensated case, and this F1 will be gone. This F1 will not be there. This will be gone, and F2 and F3 will be there. This F2 and F3. And I think I have already erased that diagram. But, no problem. Actually, I will draw it again. So what you have here is that, or I will just. Okay. So I think okay. I hope you can see how I can. I hope you can hear. So this is the cutoff the break frequencies F1, F2, and F3 for uncompensated case. Okay. So when you are having that compensation, what will happen? When you are having that compensation, you will be having an additional pole. It is happening at this point. You will be having an additional pole F0 over here. So this is with the compensation. This blue color with the compensation, and with the pole 0, pole 0. So from here, it will start decreasing by minus 20 degrees per decade, and just drawing parallel to this line as this minus 20 degrees. This is representing it. So even though it reaches at F1, remember that initially when it in the previous case, as I explained, when it is coming and when it reaches at this F1, it will start again uh, there will be one more break frequency and it will start decreasing by minus. Okay. This is not going to happen in this pole zero compensation because F1 has removed. F1 has been removed from the system because of that pole zero compensation. So zero is also coming in which cancel the M1 nuclear. So that is not there. F1 is not there with the compensated network. So this will continue by decreasing in the same fraction by minus 20 dB per decade. And once it reaches at the F2, then it starts decreasing by 40 dB per decade, and so on. So what is the advantage of this pole zero compensation is that if you consider this F0 and if you consider the bandwidth, it is still less than that of the uncompensated case. But in this case, we'll get a bandwidth which is higher than that of the dominant pole compensation. So the bandwidth will be increased as compared to the dominant pole compensation in this particular case. That is the advantage as compared to the dominant pole compensation. But as compared to the uncompensated network, the bandwidth is still less than that. Then we have to look for the internal compensation technique, which is also called as Miller compensation, to get a wide band of bandwidth. Okay? So that we will not discuss because it is not in your syllabus. So here we have a larger bandwidth than the dominant pole. That is the advantage of pole zero compensation. Also, one more thing is that in the previous case we had this kind of a smooth variation of gain, which was restricted up to F1. Okay? It was only up to F1, then it will start again decreasing by minus 40 dB per decade because F1 is there in your dominant pole compensation. So because we are adding one more pole, but we are not taking away any of the poles in the system in the dominant pole compensation. But here we are adding one pole. With that, we are also eliminating or we are also removing one of the lower pole which is already in the system. So what is the importance of that? The decreasing after the first break frequency will be a very smooth up to a very wide range of frequency. In this case, up to this F2. Okay, so we can have a control over this circuit with a very wide frequency in a very wide frequency. So in this case, if you consider the frequencies from F0 to F2, we can have a decreasing of gain. We can decrease the gain very smoothly, which is not possible in case of the dominant pole compensation because F1 is there. And so this because of this is also an advantage to the pole zero compensation as compared to dominant pole compensation because the gain is reducing very smoothly to a wide range of frequency for increases. So that is an important another important advantage as compared to the dominant pole frequency. So here, as you know, this the F0 has that condition. F0 is less than F1, less than F2, less than F3, greater than 0. This condition has to be valid. So the first corner frequency is happened is at F0 after compensation, and after that the gain roll off with the minus 20 dB per decade, and at F equal to F1, the pole zero cancellation occurs with the rate of minus 20 dB per decade. So that is what is happening here. In mathematical formula, we can cancel each other, but here in the circuit, what is happening from F1 onwards, we already knew that if you are having a pole and a zero, what will be the function of that zero? We already drawn this poles and zeros in that word plot and what happens to that curve with poles and zeros. We already did that. But for this, at this circumstance, I will just show that. So for pole, what will happen? For pole, it will be decreasing by minus 20 dB per decade after reaching that particular frequency. So you have that pole. But you are having 0, what will happen? 0, it will be increasing with 20 dB per decade. Okay, from that particular frequency. Okay, so if you are having pole as well as 0, pole and 0 at f1, for example, you are having pole and 0 at f1. So what will happen? These two cancel each other. Minus 20 dB per decade and 20 dB per decade. Because you are having pole in that particular frequency f1. Also, we have 0 in that particular frequency. So the pole will try to decrease the gain by minus 20 dB per decade. 0 will try to increase the gain by 20 dB per decade. So that two will cancel each other. So that resultant will be that result in no change in gain. No change in gain. So the gain will be varying with minus 20 dB per decade because of this first pole F0. There is no change happens because of the cancellation of this pole and 0 at F1. At F1 we will not be having any change in that slope of this gain variation with respect to frequency. So that is what is happening. So at F equal to F1, pole 0 cancellation happens. And the rate of the gain decrease will be still in minus 20 dB per decade. This one will be minus 20 dB per decade here. This is also minus 20 dB here. So up to this F2, the decreasing of gain will be within the same range. So the R1, R2, RC, C1, C2 values are selected in such a way that the board plot possess this kind of variation. So in such a way that we have to choose all those values, and we also have to consider for a smooth variation. This is not a smooth variation again, because once it reaches at this point, we have a different variation. In order to have a smooth variation, as we discussed earlier also, as we can see from this figure, the R1, R2, and C2, these values has to be taken in such a way that it will cross this 0 dB okay, within with this slope of 20 dB per minus 20. Then it can vary. Okay, so up to 0 dB, we need a very sharp or very smooth variation of the gain with respect to frequency. Okay, then only we can treat it as a very smooth variation of gain with the frequency. Otherwise, still it is having one more break frequency and one more stop, which is coming within that 0 dB. Okay, so these values has to be taken in such a way that it is having one more pole at this point, and it is varying the gain from that pole with the rate of minus 20 dB per decade up to that 0 dB. But then only the variation. After 0 dB, not that much gain is not there, because gain will be 1 at this value and gain will be less than 1 after 0 dB. So we need a variation, smooth variation up to the value gain equal to 1, which is dB in terms of dB. So in such a way that we have to set these values of R1, R2, and C for 0 compensation interval. Similarly in this case also, we had to get this variation to 20 dB up to that 0 dB. So in the second diagram, what I have drawn here for the first example, that was for just an example, just to show you how the variation will happen. But in order to get a very good response, this variation with the minus 20 dB per decade, okay, this has to be up to this 0 dB. That variation should be up to 0 dB, which means that up to the gain value which is equal to 1. Okay, then it can deviate from that point. It can go like this. After that, it can deviate from that slope. That can go to 40 dB. 30 dB. So when it reaches at 0 dB, we need same slope from that break frequency up to that 0 dB. Then we can say that the variation is very smooth. Okay, so in the example I have drawn up to that because I have taken the slope in a different manner. Here also in this diagram also they have taken it in a different manner, but still it is just for just some kind of so it depends. It depends on so, anyway. So it has to be varied with the same rate up to the 0 dB to have that. That we have to understand around. So I think we can stop here and we'll continue. Actually, I thought to start with the next